Hello friends, so this is our second part of test series on organometallic compounds. In the first part, we have done the questions that was come in 2019 CSIR NET exam, and today we will discuss most of the questions that will come in 2018 and 2017 exam. So first of all, just try it by yourself and then watch the solution. So let's start with the first question. Identify the correct statement for BH3CO. So we have given with the three statements and we have to identify the correct statement for BH3CO. First is sp2 hybridized orbital of B except the lone pair of CO. So this is not the correct because sp2 hybridized does not accept the lone pair. Here empty p orbital accept the lone pair. So first one is not correct. Second, its mu CO value is more than that of free CO. Here mu CO is a stretching frequency of CO. So basically, the stretching frequency of CO in BH3CO is more than that of free CO, because here there is negligible chance of back bonding because ligand here is CO. CO give donation of lone pair to BH3, but BH3 is already electron deficient. It do not back donate to CO. So due to this, here is very negligible back bonding. So that's why nu CO value is more, because back bonding is inversely proportional to nu CO stretching frequency, as we discussed in our first part. So if you want to watch the first part of the organometallic questions, then go in the comment box, go in the description box and watch the video. So here this is second point is the correct. Its nu CO value is more than that of free CO. That is correct. Formal oxidation state of C is +4 in the compound. So that this is also wrong because here oxidation state is not 4. So correct answer is answer number 2. Here only 2 is the correct answer. So here 2 is the correct answer, B answer. Next question is the correct order of acceptor ability of phosphorus ligand is. So for phosphorus ligand, I already told you a trick that trick for the donor ability order is alkyl, then aryl, then alkoxide and then halide. Similarly, if we are talking about acceptor ability, then order must be reversed. At the first we have halide, then alkoxide, then aryl, and then at last we have alkyl. And if you see in the question that here they are talking about acceptor ability. So what is the order for acceptor ability? At the first number we have halide, then alkoxide. Now see in the options. In second and third option we have halide at the first number, and at the second number we must have alkoxide. So basically after watching the series we have only left with the second option that is correct for the acceptor ability of phosphorus ligands. Now next question is the structure of Re2Cl8 negative and OS2Cl8 negative are made up of 2 mlCl4 units. For these structures, which statement is correct? Statement 1 is A and B both have MCl4 unit eclipsed. A and B both have MCl4 unit staggered. A has MCl4 unit staggered and B has eclipsed. A has eclipsed and B has staggered. So if these type of complexes are given and you have to tell about the eclipsed or staggered type structure, then we have only come with the one type of solution. That is, if we are talking about the first number of compound, that is Re2Cl8, then just calculate the number of electrons in their orbitals. For Re, if we are going to transition series, this is a third transition series element. So here number of valence electron is 7. For 2Re it is 7 into 2, that is 14. And if you are going to find the oxidation state, then for 2x, because here we have two metal, So for 2x there are 6 electrons. So here we have 6 electrons and here we have total of 14 electrons. So just minus out these 6 from this 14 because oxidation state is 6 and we total have valence electron here is 14. So 14 minus 6 is 8. So we are left with the 8 electrons. So there are 8 electrons in the orbital of this complex. So if we are doing filling the electrons in the orbitals, then we have sigma, pi, del star. So after filling, we have all the 8 electrons are come in the bonding molecular orbitals. So after calculating the bond order, formula for calculating the bond order is 1 by 2 b number of electrons in the bonding orbital minus a number of electrons in anti-bonding orbital. For bonding we have 8 electrons and for anti-bonding in this compound we have 0 electrons. So basically here we are come with the bond order is equal to 4. Then we have 4 type of bonds here. First is del, pi, sigma, pi, del. So we have four bonds here, sigma, pi and del. Similarly, if we calculate for the second complex, that is OS2Cl8 2 negative, valence electron for osmium is 8. So here we have 2 osmium, so it is 16. After calculating oxidation state, here 2x is equal to 6. Then we are left with the 10 electrons. And if we do filling of these electrons, then 2 electrons will come in the anti-bonding orbital at del star. So after calculating bond order, because here we have 8 electrons in the bonding and 2 electrons in anti-bonding orbital. So here we have bond order is equal to 3. So 3 type of bonds are present here, sigma, pi and pi. So here we have only a very simple trick in which we have del bond. In the first complex we have delta bond present. Where delta bond present, that complex is always staggered, and where delta bond is absent, complex is always eclipsed. So first one complex is I think I tell you reverse. डेल्टा बॉन्ड जहाँ पर प्रेजेंट होगा वो कॉम्प्लेक्स हमेशा एक्लिप्स होगा. डेल्टा बॉन्ड जहाँ पर नहीं होगा कॉम्प्लेक्स हमेशा staggered होगा. So first one complex is eclipsed and second is staggered. So if we see in the option, in the fourth option, A has both MlCl4 unit eclipsed and B has both MlCl4 units staggered. Because in the A complex we have eclipsed, we have delta bond, so it is eclipsed, and in the B we do not have del bond, so it is staggered. So you have to remember this trick. So correct option is option number 4. Now next question is, according to Wade's rule, the cluster type and the geometry for SN9 4 negative respectively are. So first of all you must have to know that SN number of valence electron in SN, that is very easy to calculate. As if we are talking about SN9, then we have carbon series, carbon, silicon, germanium, SN, PB. PB is lead. So this is the series. So in the same group we have same number of valence electrons. So we all know very well that number of valence electron for carbon is 4. So for SN we also have number of valence electron is 4. So here we have valence electron is 4 and 9 metal atoms are present here. So 9 into 4 is equal to 36 electrons, and because of 4 negative charge, after adding 4 electrons we have come with the 40 electrons. For these type of complexes, to tell the structure, type and geometry of the complexes, you have to learn this one. For 4n plus 2 type electron, structure is closo. For 4n plus 4 it is nido. For 4n plus 6 it is arachno. For 4n plus 8 it is hypho. So here we have 40 electrons. So this is basically 4n plus 4 type of structure. Yes, it is 4n plus 4 because n value is 9 here, number of metal atom is 9. So here 4 into 9 is 36 plus 4. So it is 4n plus 4 type. So basically the structure is nido. As we see options, there is one option in which nido structure is present. So our correct answer is answer number 2. So you need not to find out the geometry if you know the correct way to calculate the cluster type. Next question is, among the following species isolobal to CH2. So here isolobal to CH2, here we have 5 complexes are given. You just have to find out that which is isolobal to CH2. So, concept of this isolability is very important. You just have to calculate the number of valence electrons in each case where you see this word isolobal. So here for CH2, for carbon we have 4 valence electron, and for 1H we have one valence electron. Here we have 2H, so here 2 valence electrons are there. Total is 6 electrons, and we have given with the 5 complexes. Let's see clearly. Cp, cyclopentadiene ring, chromium, CO2. For cyclopentadiene, their donation is 5 electrons. For this we have 5. For chromium we have 6 valence electron. For CO, for one CO it gives donation of 2 electrons. Here we have 2 CO. So donation of electron is 4. Total electrons is 15 electrons. So is it isolobal to this one? No. It is isolobal. CH2 have 6 electrons. So it is isolobal with the complex which have 6 electrons or either 16 electrons, because they are correspondingly equal to this one. So either the complex have 6 electron or 16 electron for fulfill the condition of isolability with CH2. So in the first complex we have 15 electrons, so that not isolobal with CH2. Second is CpCu. For Cp we have 5 electron, and for Cu valence electron is 11. You just have to know how to calculate the number of valence electron. Firstly, just learn out all 3D 3D 4D 5D transition series, and learn out the series name, elements name in the series. And for the first series you have to know that number of valence electrons. Correspondingly 4D and 5D series remain same as that of 3D series. Now come to second, that is CpCu. Here we have for Cp 5, for copper Cu is 11. So we have 16 electrons. So that is isolobal to CH2. So second one is correct option, CpCu. Now come to next, nickel CO2. Here we have nickel, we have 10 valence electron. For CO it is 4. That is total is 14 electrons. So it must not be isolobal to CH2. For next, chromium CO4, we have 14 electron. That is also not isolobal. For last, FeCO4, it has 16 electrons, so it is isolobal. So we have second and fifth are isolobal to CH2. Second and fifth. Now go with the options. In the first we don't have second, so it is not with the answer. In B is also not. C, second, third, fifth, and in the last we have not 5. So only C option is that in which we have second and fifth. Either we have 3 is not isolobal with the CH2, but you have to choose the most probable answer that will match the conditions of your questions. So here we are going with the answer number C. Sometimes in the exam you are going with these type of situations that all the options are not matching, but you have to choose the most probable answer according to the condition of the question. Now the sixth question is, the number of bonding molecular orbital and the number of available skeleton electron in B6H6 negative respectively are. So to calculate the skeleton electron, it's very easy to calculate skeleton electrons. Just come to the solution. For B6H6, you have to take common, as 6 is common in both B and H. So BH6 2 negative. For BH, we have boron. In boron, we have total of 3 valence electrons. One is make bonding with this H and left with the 2 valence electrons. So in the BH we have only 2 electrons for donation. So it gives its 2 electron as a skeleton electron for the donation. So here we have 2 electrons and total 6 BH units are present. So 2 into 6 plus here 2 negative charge, so add 2 here. So here we have total 14 skeleton electrons. So skeleton electrons आप इस तरह से count करेंगे that the number of donation of electrons plus the charge given on the complex. So here we have 14 electrons. So number of skeleton electrons are 14 here. Also number of bonding molecular orbitals they asked from us. So number of bonding molecular orbital is very easy. Number of skeleton electrons upon 2, because in one orbital we have 2 electrons. So divide the skeleton electrons by 2. That is 14 upon 2 is equal to 7. So here we have 7 molecular orbitals and 14 skeleton electrons. So our correct answer is answer number 1. Molecular orbitals are 7 and skeleton electrons are 14. Next question is addition of 2 electrons to the bismuth cluster Bi5 3 positive result in a change of structure type from. So this is also the concept that we discussed in our previous question SN9. So in these type of complexes you have to follow, must have to follow this one trick: 4n plus 2, 4n plus 4, 4n plus 6, 4n plus 8. For bismuth we have 5 valence electron. So 5 into 5 is 25. Here 3 positive charge, so minus 3. Here we are left with 22 electrons. As you go with the question, so this is basically Bi5 3 positive is 4n plus 2 type. This is 4n plus, as we have 22 electrons now. So value of n here is 5. So 4 into 5 is 20 plus 2, 22. So this is closo. Bi5 3 positive is closo type of cluster. And also they ask that addition of 2 electrons to bismuth cluster. If you add 2 electrons in this cluster Bi5 3 positive, then it will become Bi5 1 positive. Then after calculating number of electrons, here we have 24 electrons, and this is basically 4n plus 4 type cluster. It is nido. So addition of 2 electrons to bismuth result in the change of structure from. So firstly it is closo, then it is converted into nido. So correct answer is answer number 1, closo to nido. 8th question, an organometallic fragment that is isolobal to CH3 positive is. So you must try this question, as we have discussed isolability so many times in our questions. So just do try this question. Just pause the video and try the question. So for CH3 positive, we have for carbon 4 valence electron, for H we have 3 and minus 1. Here we have 6 valence electrons. So for isolability, they must have 6 electron or either 16 electrons. After calculating in all the compounds, we are having this complex compound having 16 electrons. So this is isolobal to CH3 positive. So correct answer is answer number 3, CrCO5, that we have 16 electrons, and in CH3 positive we have 6 electrons. So they are isolobal to each other. Next question is choose the ISO electronic pair among the following that are isoelectronically equal. They have equal number of electron pairs. So just go with the solution. Here we have VCO6. For V we have valence electron is 5. For CO it is 12. Total is 17 electrons. In the second, copper we have 11. For N5, here hapticity is 5, so it gives 5 electrons. So 5. For CO it is 2. Total we have 18 electrons. In the third, cobalt we have 9 valence electron. For CO it is 8. Minus 1. We have minus 1 charge on the complex, so just add out minus plus 1. So it is 18 electrons. So in the last, for iridium we have 9 valence electron, for chlorine it is 1, for CO it is 2, for ppH3 it is also 2. Here we have 2 ppH3, so total of 4 electrons. So after adding we have 16 electrons. As you see clearly, we have these two options that are isoelectronic to each other, that have same number of electrons present in their structure. So second and third are isoelectronically equal to each other. So here we have answer number B, second and third, that have equal number of electrons. Our last question is the correct increasing order of CC bond length in the following molecules. CC bond length. So firstly you have to draw the structure for this complex. In the first we have PT, Cl3 are 3 ligands and CH2, CH2 present here with the one double bond between them. Second we have PPH3, 2 ligands, and at last we have this type of structure. So basically we have to find out the bond length of CC. So this is the concept of back bonding as we see in this complex. We have double bond between CC and CN ligands are present around 10. As CN attract electron withdrawing, they attract electron density towards each other. So this one is electron deficient. This part is electron deficient. So it must try to accept electron from the metals toward itself. So there is more back bonding, and more the back bonding, more the bond length between the ligand CC. Lesser the bond strength but more the bond length. So we have C option that have more bond length, and in our options we have only one option with C as the higher bond length. So due to the electron deficient compound as CN, it make it more electron deficient, so it attract more from the metal atom and it undergo better back bonding, and due to better back bonding the bond length of CC bond increases. So that's why we have B option as our correct option. So guys, we have discussed most of the questions on organometallic chemistry, and we also come with third part of for the organometallic, in which we do further questions on this topic. So just continue your preparation and do practice more and more questions. Try to solve it 2 to 3 times. If you have doubt in any question, and if you are willing to ask anything, then please put questions in the comment box. Thank you so much for watching, and if you like, then please subscribe the channel.